We came to a rather abrupt end on that one. I guess I should be watching the time a little more closely. Anyway, so we talked about ray number 1, and we talked about ray number 2 that goes through the focal point. Let's now look for conditions ray 3 and 4. Ray 3 is one right here that goes from the top of that object through the center of curvature and hits here, and it's going to come directly back on that same line, right? Reflects, returns along itself. A ray that reflects from the mirror, okay, at and this is at point number 4 right here, and it goes to the point that's on the center of the line of axis here, that's symmetrical about the axis, comes directly back out and reflected like this, so that this angle is going to equal this angle. Okay, so and here's where the object is right at that point right there. So anyway, and then the same type of considerations you can have for something here, where you have an object that comes in at the object point here. It's going to be reflected out here. It's also going to go down there, and from this, and also for from here, it's going to come back out this way right here. On this one right here, you've got 3 that appears to be coming from that point right there, and essentially 4 goes here out to here, right? So anyway, there's interesting geometry for locating images by drawing rays on these different ones. So checkpoint number 2, a Central American vampire bat dozing on the central axis of a spherical mirror is magnified by m equals -4. Is the image real or virtual? Okay. It's a spherical mirror, and the image is real. And is the image inverted or the same orientation? And the image would be inverted, right? And is it on the same side of the mirror as the bat or on the opposite side? It's on the same side of the mirror as the bat. All of those you can tell because this is a -4 for the m. Remember, m equals -I over p. Okay? The fact that it's a minus sign here means that it's a real image. Okay? And the fact that it's a spherical type of mirror, it's inverted, okay? And it's on the same side of the mirror. Okay, this is practical exercise number 3. This is problem number 6 at the end of the chapter. An object is moving along a central axis of a spherical mirror. The figure gives the magnification. Here's how much it's magnified, right? Versus the object's distance for the range PA, right here it's at 2 centimeters, out to PB. What is M for 14 centimeters? So I want you to extrapolate out. So when you do that, remember, M equals, we'll see how they do this. Yes, M equals 2 equals -I over P, and that's going back and getting at this curve right here. So m equals 2 at this point right here, okay? So, and this right here is PA, well, this point here is P at 5 centimeters, okay? This is 2 centimeters, 3, 4, 5, 6, 7, 8. And so at this point right here, you've got the ratio, the value of that at that time, okay? So it equals 2 -I over P equals -I over 5.0 centimeters. So I equals -10 centimeters. Then what you do is you use this equation right here, the lens equation, and the focal point, right, for what it's going to be at some other point out there. So here it's 1 over 5 centimeters, okay, plus 1 over minus 10 centimeters equals 1 over 10 centimeters. So F equals 10.0 centimeters. So that's what we have to determine the focal point first. Then once you have the focal point, you then determine what it is for P. So it's going to be 1 over 10 equals 1 over 14 centimeters. And now we can solve for I, right? So 1 over I is going to be 1 over 35.0 centimeters. So the magnification is going to then be 35 centimeters over 14 with a minus value there, right? And you'll notice that in this particular one, that it ends up being a positive sign on this, right? Okay. Yeah, on here, I actually calculate, my I would have been 34.5 centimeters there instead, okay? And so on I would have gotten 2.46 here using these numbers. But if you're going to have three significant figures, it really should be 34.5. And this one right here for two significant figures, well, yeah, I guess 2.46 would be 2.5. Okay. So anyway, practical exercise number 4. This one right here is problem number 8. An object is placed against the center of a spherical mirror and is moved 70 centimeters from it along the central axis as the image distance I is measured. The figure gives I versus the object out to 40 centimeters. Okay, so this would be 10, 20, 30, 40 centimeters. What is the image for the point 70 centimeters? And again, we're working with, from the graph right here, you can see that the focal point is going to be right here. It's going to be at 20 centimeters, right? So when this goes to infinity here and this goes to infinity here, that means this right here is the focal point. Okay? So that is from the graph. You determine that. You then utilize that in this equation right here. Same one we had, 1 over P, 1 over I. So this is going to, this right here we determined was 20, so this is 1 over 20 centimeters equals 1 over 70 plus 1 over I. So this means that 1 over I is going to be 1 over 20 minus 1 over 70. And yes, it does turn out to be, that's 50 centimeters over 1,400. And I did get 1 over 28 centimeters. So that I then equals 28 centimeters. Okay. A lot of times they're leaving them as fractions. I actually did the calculations out to make certain that the fractions were right there. Now we're going to talk about spherical refracting surfaces. Before we were talking about reflection, but what happens is if you have a medium that is of a different refractive index, then the light, instead of just bouncing back or when it goes into there, showing up as an image, it's going to be changed because of that refractive index. So it's going to be shifted some. So a single spherical surface that refracts light can form an image, right? An object distance P, the image distance I, the radius of curvature R for the surface are related by this right here. N1 over P plus N2 over I equals N2 minus N1 over R. These N's refer to the index of refraction of the material. Okay, air is usually taken as 1.00, where the object is located, and then this is of the other side of the surface. If the surface faced by the object is convex, R is positive. If it's concave, R is negative. That's an important thing to remember in that convention right there, okay? Real images form on the side of the refracting surface that is opposite the object. Virtual image is formed on the same side as the object. So an image formed over here is going to be a virtual image. An image formed inside is going to be, well, this is right here is the image and the object are on the same side. Okay, but something that is formed over here is going to be a real image, okay? And it's going to be virtual on the same side as where it's refracted, okay? So checkpoint 3. Here you have B that is hovering in front of a concave spherical refractor of a glass sculpture. Which part of figure 34.7 is like the situation? Okay. And in other words, it would be a concave type of situation, right? So the concave means that it would be more like this one over here, wouldn't it? Okay. So here you have your object and your image, and all of that is going to be on this side. And so it's going to be like this. So what this means is that the image is going to be over here, so it's going to be virtual. And then what was the third part of that? Is it on the same side as the B or the opposite side? Well, as we saw in this diagram right here, it's on the same size. Okay? Well, and the reason the image is virtual and on the same side means are essentially the same thing. It has to be virtual if it's on the same side. Okay? Okay, practical exercise number 5. Here we're talking about problem 34, and you've got beams of parallel light rays from a laser incident on a solid, transparent sphere, and their index of refraction of this sphere is n. If an image is produced at the back of the sphere, back here, what is the index of refraction of the sphere? What index of refraction, if any, will produce a point image at the center of the sphere? Okay, so the n1, where it's coming from, is the n of air, so that would be 1.00. n2 equals n. Point is at infinity, and I equals 2r, right? That's what that would determine. It's going through the, this is one r, this is the other r over here, radius of curvature. So n1 over p plus n2 over I equals n2 minus n1 over r. This one right here, p is infinity right here, so that's going to be 0. This is going to be n over 2r. This is n minus 1 over r. So n over 2r equals n minus 1 over r, so that n over 2, and because essentially what you've done is you've just taken the r's out, you multiply both sides through by r, gives you this equation right here. So n equals 2n minus 2, or n equals 2.0. For part B, so if I equals r, you then have this right here, okay? So it's 0 minus 1. It's impossible to focus at the center of the sphere, okay? That's what that one turns out to be. Now we're going to talk about thin lenses. For an object in front of a lens, the object distance p and the image distance I are related to the lens focal length f, the index of refraction, and the radii of curvature, r1 and r2. This is called the lens maker's equation. Okay, this is thin lenses in air. The radius 1 is the curvature of the lens nearest the object. R2 is the other surface. Okay, so this one is the one that's nearer the surface. This is the other one. If the lens is surrounded in some medium other than air, say corn oil, with an index of refraction, we replace n with n over n medium. The lens can produce an image of an object only because the lens can bend light rays, but it can bend light rays only if the index of refraction differs from that of the surrounding medium. Okay, so if it's no different, it's not going to bend any light rays. It's the light rays bending that causes the image of the object. Okay, that's the critical thing there. And you can actually form some of these lenses by just putting a droplet of oil and over something you want to magnify, and you can see that works. So that's going to be the end of this particular section.